Hello everyone. This is another lecture of quantum mechanics, number 27, and we have so far studied like till quantum tunneling, and we'll today discuss some problems which will discuss only the working principles. All right. Now let's start with the today's lecture. Okay. So what we'll do is we'll take out some problems today and see how to solve them. All right. These are some typical problems which I'll discuss the theory and then do the problems. All right. And were you able to solve yesterday's problem, homework problem, or you didn't try it? So let's discuss something called problems related to sudden change in box size. Okay. Problems related to sudden change in box size. All right. Now let's consider a 1D potential well. Let's consider a 1D potential well. All right. And so this is Vx equal to infinity. And now let's talk about, say the particle is in the ground state of the well. Okay, this side is also infinity. Let's say the particle is in the ground state of this potential well. Okay, so this is L by 2. All right, now let's write down this statement that the initial condition, the particle is initially in the ground state, okay, of 1D box potential of width L. Potential of width L. Okay. Now this is the initial situation. Now what happens is suddenly, okay, it has to be abrupt so that the wave function of the particle does not change. But what happens is suddenly one of the walls of the box potential is shifted to a new position. All right, suddenly one of the walls of box potential is shifted to a new position. Now what happens in that situation? Now the question is asked that, okay, what is the probability that the particle could be found in the ground state of the new potential? Once you shift one of the walls, what happens is there's a change in the wave function as well as the change in the energy eigenvalues. There's a new potential altogether. But because the walls have been shifted suddenly, uh, there is the wave function of the particle does not have that much time to change. Okay, so the wave function of the particle remains intact as it is, as in the initial stages. Okay, but the box size changes, and when the box size changes, the potential completely changes, because the energy eigenfunctions is affected, energy eigenvalues are affected. All right, so the question is asked that what is the probability of finding the particle mm, inside the new potential in the ground state. All right, so what happens, how to solve this? So the question says, now in this case, if you note down the wave function in this case, which is psi1, say the ground state, this is at 2 by L, root 2 by L, sine n pi x by L. All right, so now the question says, what is the probability, what is the probability okay, of finding of finding the particle in the new ground state, in the new ground state, in the new ground state. Now this question is not asked in JAM. All right, this question is not asked in JAM. This question is from the point of view of just TIFR net gate. All right, these questions, whatever I will be discussing today. Now, so the question remains this. All right, now what happens? Let's see how does the wave function looks like. What is the change here? Okay, so this is, say, the initial potential. Now this was the initial potential. Let me draw it again. So this was the initial potential. Now the wave function was this. Okay, the wave function was this. It was in the ground state. So the wave function looks like this. All right. Let me draw it correctly. Okay, whatever it is. I hope it makes sense. I cannot waste time on this. Okay, so this is 0 and L. Now let's say the box is doubled. Okay, it has moved to this position. It has been shifted. Now this is a sudden shift. Now this has been shifted suddenly. Sudden shift. If you move slowly, then the particle will adjust, the wave function of the particle will then adjust itself and conform to the new one. But in this case, the wave function does not change. The particle, the wave function remains the same as the previous, okay, in the initial stages. So final box size, final box, okay. Now in this case, the new wave function is, now in this case, the potential is defined by this. Okay, this is a new potential. So let's label it Vn. Okay, and this is a 0 for x lying between 0 and 2L, and it's infinite otherwise. So this is the mathematical representation of the new well, and the wave function, let's say it's called at phi n, and the new eigenfunctions are given by, this is the normalization constant, and then we have n pi x by 2L. All right. Now, the initial wave function is here in this case is psi1. Initial wave function of particle is psi1. All right. Now, due to whatever argument I gave you, let's note it down. Due to sudden change, in box potential, okay, the wave function the wave function of the particle of the particle does not change. Clear? Now, what happens is that we can now since the particle wave function remains the same, so it can be represented, the particle wave function, initial wave function can be represented in the new as a superposition of wave function of the new well, right? So since this wave function in the new well cannot be represented using the pure states, only a single pure state, it has to be a superposition of several states, okay, in the new potential. So we can expand now. Let's write it down in. We can expand. We can expand the wave function. The wave function. Okay, psi one in terms of mu eigenfunction. Mu eigenfunctions. All right. So now the question was that probability of finding the particle, probability of finding the particle, finding the particle in the ground state, in the ground state, okay, of the new potential, of the new potential. Okay, we have already done this previously. We had talked about it. So I want to find out the C1 mod square. How will we do it? Just take a inner product of the phi 1 with psi 1 and then mod square. All right, so this is the thing you need to remember, that if you have been given a well where this thing is changing suddenly, there should be a sudden change, okay, and the question will mention this. There's a sudden change in the dimension, and then that changes the potential to a new well. So in that case, if you want to find out the probability of finding the particle in the new ground state or any other state, okay, you need to do this one. All right. So what we have here, so in this case, you already understand this thing, right? So I'll just repeat it once. So what you do when you like do an inner product of phi 1 and psi 1, so what you do, like you take this phi 1 and place this C1 phi 1 plus C2 phi 2. All right, now this becomes, this is the first term is C1 phi 1, phi 1 with inner product with phi 1, and then we have C2, then we have phi 1 inner product with phi 2. All right, now it goes on like this. So we have this similar term, the same term, there is cross terms out here. Okay, so these this will become, this is equal to 1 and this is 0, and so on, like all the terms will be 0 further in this case. So phi 1 plus inner product with psi 1 is equal to C1. All right, so all right, now if the particle, initially, now let's quantify, let's look at it in another way. If the particle is initially in the state psi I, okay, let's say it's in the psi I state, Now after the sudden change, after the sudden change of the box size, of the box size, all right, the probability of finding, the probability of finding the particle, finding the particle in the final state, in the final state, all right, psi f of the new potential, of the new potential, all right, is, now this is given to be this, so we have psi f and we have psi I, all right, this is mod square. So this is the same thing which we have already written earlier. I just took an example of the ground state. Okay, in this case we are taking it to be in any state we want to find out. Okay, so this is what we have here. All right, so this is the thing you must remember. Now you already understand, like it's when you I just give you an example in previous lectures about how do you find out the coefficient along of the unit vector in a given vector. Okay, we just dot product, use a dot product to get that thing. You can just by observation you can get it, but in this case the observation is not possible in that way, that you cannot separate it and write it. If you are able to write it directly, then you don't need to do the calculation, but it's not possible to write the wave function in a superposition this way. Okay, the ground state in the new wave function format. Okay, so it's better to use this one. Now let's look at a problem. Okay, so this problem says, now this is a question from uh, just 2019. Okay, so the question says, consider a quantum particle, consider a quantum particle of in a one dimensional, in a one dimensional box of length L, box of length L. Okay, the coordinates, the coordinates of the left, of the leftmost wall, or the leftmost wall of box, of the box is at x equal to 0. All right, and that of the rightmost wall, the rightmost wall is at x equal to L. Now the particle is in the ground state. The particle is in the ground state. All right. Now at t equal to 0. Okay. Now at t equal to 0, suddenly we change the length of the box. We suddenly change the length of the box to 3L by moving by moving, okay, the right wall. All right. Now, what is the probability? What is the probability? What is the probability that the particle is in the ground state, okay, of the new system, of the new system, okay, immediately after the change, immediately after the change. All right. So this is a question. Now this is a question from just 2019. You will find similar questions in GATE and NET. Okay. So let's try this out. Let's look at it. Now the options given to you are in the are as follows. A is 0.36, B is 9 by 8 pi, C option is 81 by 64 pi square, and D option is 0.5 L, 0.5 by pi L. All right. So let's see how can we solve it. Now let's, so have you written down the questions? The question, is it clear to everyone? Okay, so let's draw the potential and see what is happening here. So in this case, you have the potential to be, say, of this size, and this is Vx, which is infinity, and Vx, which is infinite here, and Vx is 0 here. This was the initial potential, and suddenly what happens is this potential becomes, the width of the potential becomes 3 times. Okay, so this is Vx equal to 0. Now this is of course not to scale. Now this will become, look, 3 times the size of the initial one. Now this is also Vx equal to 0. Sorry, not 0, infinity. Now this is 0 and this is 3L. All right. Now initially, now the initial state, now eigenfunctions of, now the initial state of the particle was, initial state, say psi 1, which is 2 by L sine pi x by L. All right. Now in this case, the final state, now what are the eigenfunctions for this? Now eigenfunctions for this is phi n, and this will be 2 by 3L sine, okay, 2 by 3L sine, and this is n pi x by 3L. Okay, so this is the new eigenfunctions, and in this case the eigenfunctions we know already. So we have phi 1, the ground state in the new potential will be this. All right, so this is sine 3 pi x by L, sorry, 3L, not 3 here, this will be, this is pi x by 3L. All right, so this is we have both the states. Now probability of finding the particle, probability of finding the particle, in the new ground state, okay, is given by phi 1 psi 1 inner product mod square, right? So just it, what we have to do is we have to do the integration. All right, so everything boils down to this thing that we have to do the integration. Now this is phi1 and psi1. All right, so 0 to, now we'll integrate it from 0 to L because the wave function is 0 for the rest of the interval. Okay, we could have mentioned 3L here. Okay, we could have taken the limits for using the new L, but it's no use. All right, because the wave function, this psi1 is 0 for beyond L, x equal to L. All right, so we'll limit ourselves to this limit. So this, let's write down this. Now these are real wave function. There's no need to conjugate the thing. Even if you conjugate, you'll get the same thing. So we'll just write down the functions as it is. So this is pi x by 3L, and we have this part which is sine. Now there will be a constant factor also, which is root 2 by L. Okay, sine pi x by L. Okay, this is dx. Now this, just rearrange this thing. The let's take out the constants here. Now this is the constant which will be taken out, and we have sine pi x by 3L, and this is sine pi x by L. Okay, if we integrate this, if you just try to integrate this, so it's, let's take out the 2, let's use the 2 inside. Okay, let's take the 2 inside and use it to convert this to a superposition form, okay, of two functions. So we can write this 2 sine A sine B, right? It's like 2 sine A sine B, so it's like cos A. So this is this minus this. All right, and we have minus cos, this is A plus B, right? So this is cos pi by x plus pi x by L. All right, dx. Right, now next, let's see, let's calculate this further. Now this is 1 by root 3L. This will be 0 to L. Now let's simplify this. This cos, this will be 2 pi x by L. All right, minus cos 4 pi x by 3L. All right. So I hope everybody is getting this thing. Now root 3L. This, now let's integrate this. So this will be 3. Now this is, now there will be a 3L right here. I missed this thing. So this is 3L by 2 pi. This is sine. This will be 2 pi x by 3L. All right, 0 to L, minus 3L by 4 pi sine 4 pi x by 3L, 0 to L. All right, now this gives you, now this is all integrated, like it's just simplification further. So this is 3L by 2 pi, and if we write this down, so what will we get? Now 0, the lower limit in both cases will be 0. Okay, so upper limit will be 2 pi by 3, and in this case the upper limit is 4 pi, and this will be, this is 4 pi by 3. All right, this is what it simplifies to. Now if we just 3L by 2 pi, now this is what, this is root 3 by 2 minus 3L by 4 pi, this is minus root 3 by 2. All right, so if you solve this thing, so you'll get 3 by 4 pi. Now L term gets cancelled, so we have 3 by 4 pi plus we have 3 by 8 pi. So if we write this down, there's 3 by 4 pi and 1 plus 1 by 2. Okay, so this is 9 by 8 pi. So if you want to see how, like what, how do we get root sine 4 pi by 3, you can write 4 pi by 3 as sine pi plus pi by 3. All right, So this becomes minus sine pi by 3. Now this becomes to the third quadrant, so the sign is negative there. This is minus root 3 by 2. All right. So I just used it directly. Now what we wanted is the probability. The required probability was this. So we had pi 1 psi 1 square mod square. So 9 by 8 pi mod square. Okay. So 64 pi square. This is the answer. All right. So just 2 lines of physics and rest mathematics. So you cannot forget the conversion formulas in trigonometry. Okay. Otherwise, you'll make a mistake. All right. So I hope you have like you have to solve these kind of problems in this following manner. All right. Now the next one is yes.
So why we have used in the limit here from 0 to L?
I
Because in
told
the
you.
final state the boundary is 0 to 3.
Yeah, I already mentioned this thing. If you if you
If you
see
kindly
the
explain again.
sorry. So
If you
in this
kindly
case,
explain.
if you use 3L also, let's put it to be 3L. Okay, let's put it to be 3L. So if you see this wave function, this wave function, this wave function is from which limit to which limit? This is between x going from 0 to L, right? And for x greater than 0, this wave function, the psi 1 is 0, right? So if if we integrate from 0 to 3L, this wave function only exists for 0 to L, the initial ground state. All right. So it will become
Okay.
0. All right. I told you this earlier also. So this will become 0 in any way. So it's better if we integrate from the limits which is for the initial well. Okay.
Thank you, sir. Got
Yeah.
it.
Now the next one is now. So these are some different like we are not getting into details of it right now. Okay. So just the working principles, how to think, just solve the problems in these sense. But the previous problem was, of course, everything was defined clearly. Now we'll talk about matrix representation of wave function and operators. Okay. Of now we are not going to prove it and derive anything here. We are just going to see how to use it. Okay. For you can of course always look at Jetili for the derivation if you want, for the theorems you want to look at. Okay. But in this case, since the time is limited, we'll just look at how to use them to solve the problems. Okay. So this is the ket vector. Everybody knows it. Now this is represented using a column matrix. This is a column matrix or a column vector. All right. Now in this case, we represent, say, like this. This is psi 1, a1, a2 dot, like, goes up to an. Okay. Now in this case, ais, okay, are complex numbers. Okay. Complex numbers. All right. Now the bra vector. Now this is the bra vector. Okay. This is the bra vector. Now this is represented using a row matrix. Now it will be obvious in some time why we are representing this using a row and the other one as a column matrix. Now this is actually this is the bra vector can be given as you can just find it out using the, if you take a dagger of the ket vector, you'll get this. So it has a conjugate as well as a transpose. So if you transpose this ket vector, which is a column matrix, it will give you a row matrix, and you'll have to conjugate all the terms inside. So all these terms are conjugate, and this converted to row matrix. Okay. Now for a example, if you look at it, so for a two-level quantum system, for a two-level quantum system. All right. So you have this thing. We can represent psi, the wave function of the particle, is as this, as a 2 cross 1 column matrix. Okay, and similarly the bra vector, corresponding bra vector, will be a row matrix of size 1 cross 2. Now if we try to find out this inner product, okay, inner product of psi with itself, so we'll do like this. Okay, this is the row matrix. You have a column matrix. All right, so this gives you a1 star a1 plus a2 star a2. All right, so this is basically what? This is basically the inner product, which we have already seen, which gives you a1 mod square plus a2 mod square. So you can see here that now this was similar to what we have done. Like if you remember this, that if when we took this thing, like it was c1 ci mod square, right? I going from 1 to n. So it's it's the same term. So these you can understand that this a1 and a2 are the probability amplitudes. Okay. All right. Now the operators. How does the operator look like? Okay. How does the operator look like? Now operator are square matrices in this case. Okay, the operators are square matrices. They have this form, which is say a11, a12, all right, going up to say a1n, and we have here a21, a22, and this goes up to this point, and then we have along this one we have an1, and then so we have similar terms. So this last term will be this corner term will be, now let's take it to be m, not n. Okay, m1, this is mn. Now I'm writing a general operator here. Okay, mostly what you'll use is a square matrix, but I'm writing it for a general thing. Now an operator is represented as a square matrix. So for those who are very curious about how this is happening, okay, you can always look up Jetily for this. Okay, how can we write the operator in this format? Okay, so so this a11 is actually this. So this is the, say, the first state or whatever it is, the ground state. Now this is how it represents. The a11 term is actually this. It's a expectation value of a in this state. Okay, so where n and m, okay, are orthogonal to each other. So these states are orthogonal to each other. So we are representing it using this notation. I hope that you're comfortable with this notation by now. Okay, now a n m in general term. So this will be this inner product. Okay, now all right, can find out all the terms like this, all the terms of the operator like this. Now let's take an example. Consider a two-level system. Consider a two-level system. Say we have this situation where we have these wave functions phi1 and phi2. Okay, phi1 and phi2, and these are and the operator is given by this. Now we have operator. We have an operator which is given by a cap is equal to this one, and then we have this, right? This is how we are defining an operator in Dirac notation. Now this is the operator in Dirac notation. Okay, operator in Dirac notation. All right. Now these kind of products have a meaning in itself. We are not getting into that, but we are just using it to see how to work with it. Okay. So in this case, this A operator will have a matrix size. This is of dimension 2 cross 2. Okay. So we'll write like this. This is the matrix required for the operator A. And say we want to find out what are the eigenvalues of this operator. Okay. What are the possible eigenvalues? So we try to find out the matrix first, and then we know how to calculate the eigenvalue from a given matrix. Okay. So A11 is equal to 1, the first state. Okay. Now these labels could be changed. Instead of 1, it could be 0, 0. But then this notation has to be accordingly not change. You cannot change this because this thing represents the index in the matrix, the element index of the element in the matrix. Okay. So if we have been given 0, 0, so just change this. You don't need to change it. You have to understand that the 1, 1, this one will become 0 instead. Okay. So because in harmonic oscillator we have a 0, we represent the ground state using a 0 ket. All right. So in this case we have 1. We can, how do we find this out? So we have this state, and what is the form of the operator here? This is given to us, this as this. All right. Now when we sandwich this, we are like putting this together. Now let's take this element and take this term as well as this term. Okay, the first thing. So what do we have here? We have 1, 1. Now this becomes inner product with this one, and this becomes inner product with this one, rightmost ket. And then the second term is this is a inner product here, and then this becomes an inner product on this side. All right. So if you see, this is 1, this is 1. So see, we have already mentioned there are 2 level systems. So that means 1 and 2 states are orthogonal, orthonormal. All right. So we have ones, and in this case we have 0. So the A11 matrix element becomes 1. Okay. Similarly, we can find out other ones. So you can calculate it yourself. So this second term, second element is this. So we can write like this. So if you can directly write it down if you want. So I'll just do it on the screen. Just check it. All right. So we have this now. This is a 2, not a 1. Right. So this is 2. So in this case, what happens? This the first term will be 1, 1, and this second term is 2. This is 1, 2. This is 2, 2. All right. So this is 0, right? And this also becomes 0. Although this first term is 1. Okay. So this is not triple 1. This is so this first term is 1, but this term is 0, and this term is 0. This is 1. So nothing, like everything becomes 0. All right. Similarly, if you find out A21, okay, A21, I'll not write it everything right now. Now you understand how to find it out. Okay, so we'll have these terms. We have now I'm directly writing it down. We'll have these terms. Okay, plus 2, 2. This will be 2, 1. Okay, so in this case, this also becomes 0. Now sorry, there won't be a 3 here. This is 2, 2. So if you write this term down, this will give you again 0, right? If you write down the terms, these are the terms which you get. Not 0, if you will get a 1 here, because we have a term which will survive. All right, so this is what we have here. Okay, so this gives you, this is 0, this is 1. Okay, both the terms are 1, so we have 1 here. All right, so finally we have the matrix here. So let's see. The matrix looks, the operator matrix looks like this. Is 1 0 0 1. Okay, now you can find out that eigenvalue from this for the given uh, quantum system for this operator. All right, so this is the answer we are looking for. Now let's take a question from Jest. All right, so this one is a question from Jest. Let me write it down. So the question says, if a Hamiltonian, if a Hamiltonian H is given as is given as H equal to 0 0 minus 1, all right, plus iota. Okay, so we have this let me write this down together at in one place. So H is given by, this is 0 0, all right, minus plus. Now we are not discussing this form, this product form. This I'm restricting my discussion to just using the method to solve the problems. Okay, like these have also names, these kind of products. Okay, so this is the this is the Hamiltonian given to you in operator format. Okay, using the Dirac notation. So this is where 0 and 1 are orthonormal states, are orthonormal states. All right, and the eigenvalues of H are, the eigenvalues of H are, you need to find out the eigenvalues of H. So A option is plus minus 1, B option is plus minus iota, C option is plus minus root 2, and D option is plus minus iota root 2. All right, so this is a question from Just 2015. Now similar questions are asked in Just all like in net also and get also in TF also. Okay, so I have taught you how to use this thing. Now in this case, let's keep the matrix like this. Let's define the matrix like this. H is already given to you. Now let's say the H is the matrix is like this. Say H 0 0. Let's start the index from 0 0 because it's easier to keep track with the state names. Okay, state labels. So we have this matrix. All right, now it's given that 0 and 1 are orthonormal. Okay, this is given to us, and the Dirac notation format of the operator is given to us. So we need to find out the elements before we can find out the eigenvalues. So the first element will correspond to this. This is, so the matrix does it's not written as a this thing. Okay, sometimes it's written with the hat, sometimes it's not. All right, so in this case, let's see this thing. So 0, we have the operator. Let's write down the operator, which is 0 0 minus 1 1 minus iota. Okay, so there is a plus sign or a minus sign. There is a plus sign. Yeah, there is a plus iota. All right, So we have this thing, we have 0, 1, minus 1, 0. Okay, and this one is like, I have to shift a little bit to the right to make some space. So we have 0 here. Now if you see the terms, so what terms do we have? So we have this first term as this, second term as this, and third term 0 0 is 1 0. All right, minus iota, this is 0 1, and then we have 0 0. All right, so I hope everything falls in line, like yeah, all the terms are okay. Now let's write it down. So this the first term is 1 and 1. Okay, this is 0, the second term is 0 0, because there's this orthonormality condition. By that condition we get the 0. Now we have here, this is iota 1, and then the next term is 0. Then in this case iota we have 0 and 1. All right, so this gives us 1, right? So everybody is getting this result. Now similarly, if you write this down, 0 1, okay, so in this case you can see directly for yourself which term will survive, which term will not. So if you see, look at it closely, you take the operator from here and you see that it has a 0 and a 1. So we have to see which has 0 and 1. Okay, so 0 and 1 in this format will survive only. So we can directly write it down. So first term will become 0, second term will become 0, third term become iota, then we have 0. Okay, so we have to have a term so that uh, we we can get a 1. Okay, in our inner products. All right, so if you see this, for this this element, if you just see this, which will survive is this term. All right, this term will survive. So you can figure this out for this kind of you can just have a picture in mind. If you want this term non-zero terms, so you have to look for terms for the elements in the operator as this. Okay, you have to look for this term in the operator. So this term will only survive. All right, other terms will become 0. Right, you understand why? Because the inner product will survive. Okay, so this is you can note this point. All right, this is how you can look at it without writing down the whole thing, and you do not make a mistake. So it's better to think of it in this way. So h, now the next term which we'll discuss is h10. Now in this case it will become this, and which term will survive? The term which will survive is from the operator will be 1, and this is 0, right? This term we should look for this term. So let's see which term it is. It is this term, right? This one. Now, so we have to look for this term in the operator, and then figure and just directly write it down. So we have, if this term survives, we have a minus iota. Okay, we don't need to write it down, or let's write it down so that you have a this thing, that this 0, the first term, this will be 0. This other terms will be 0. Only this term will survive. Okay, this is minus iota. Now h1,
Sir,
yes.
in the last term there is no it, right?
No, there is a common, na.
Oh, sorry.
This is a common term. This has been written in a bracket. Okay, there is a iota for in both the terms. All right. So you have this thing. So you can write. Now now already understand which term to look for, which will survive. So the term with this for operator, uh, okay, this will survive, right? Now just look for it. So you can just look at the this thing operator. So which term it is? It is the second term in the operator. So we can just directly that the other terms will be 0, and the second term will survive. Okay, because the inner product will become non-zero. Now this is what we have, as this is -1. Okay, so we have to look for the term, this one in this case. So you understand how to build a search for this term from the given element notation. All right, now h H is given to be, now we have all the elements in place. This is 1, this is iota, and then we have -1, this is minus iota. Okay, now everything now is all, we can just simply calculate the eigenvalues, okay, from for this matrix. So the eigenvalues we can calculate now. 1 minus lambda, I hope everybody knows how to calculate the eigenvalues of a matrix. Okay, so you take a determinant and put it to 0, where lambda is the eigenvalue. Now if you solve this problem, so what you get, if you solve this further, now open the determinant, expand the determinant, you get this -1 equal to 0, and further we have 1 minus lambda square, -1 equal to 0. So this is -1 plus lambda square -1 equal to 0. Okay, so this gives us lambda is equal to plus minus
So,
√2. Yes.
so in the the H10 is minus iota.
Did I make a mistake here? H10. Okay, okay. Yeah, yeah, you're right. You're right. I just misplaced this thing. You're right. This is minus iota, and this is -1. Yeah. Actually, I meant to write that only. I just misplaced the things. Okay. So this is the answer what we have for the question. Oh, see, I wrote this here correctly. The terms here, I've written them down correctly. Okay, so this is the correct answer, C option. All right. So let me give you a question, and we can discuss yesterday's problems also. Now this question says, given psi is equal to, now this is the example problem. You should understand how things are calculated here. So this is 5 iota, 2 iota, and we have phi given by this thing 3, and we have the phi is given to be 8 iota here, 8 iota, and we have a -9 iota. All right, so this is the way the two column vectors given to you. Find psi star, okay, and psi. All right, and next question is psi normalized? Is psi normalized? Okay, if not, normalize it. Normalize it. Okay, so I'm all right. Now next question is, are psi and phi orthogonal? Okay, so you have to check for this. So let's do it quickly. Okay, you have the question given to you. All right, so the first part, we want to find out psi star, okay, psi conjugate. So this is simply, you take all the terms, we just put iota to minus iota, and we have the terms. All right, so this will be minus in this case. Okay, now I think there is a missing sign here. This will be minus, this will be plus here. So this is what we have. All right, in the question you make a correction, there's a minus iota here. All right, now if we do this thing, we get this, right? Now what is if you write down psi, if you try to get the bra vector from this, okay, so this will be like this, psi, all right, equal to psi, this is the dagger, we have minus 5 iota, 2, and then we have a minus. Now we have a conjugate as well as like we have a transpose as well as a conjugate. So we get the row matrix. All right. So this is the answer which we are looking for. Now the B part, it says that okay, whether we have to check whether psi is normalized or not. Let's take a inner product. Let's calculate the inner product. Okay. So the inner product is like this. So we have 5 iota minus 5 iota, 2, this is iota. All right, and then we have 5 iota, this is 2 minus iota. All right, so this gives you minus 5 iota, and we have 5 iota here. Okay, then we have 2 plus we have iota as well as a minus iota in this. So the terms which we have here is 25 plus 4 plus 1, so this is 30. All right, so this is not equal to 1, right? So that means this is not normalized. So how will you normalize this? So the normalized psi will look like this. So this is not, psi is not normalized here. Psi is not normalized. Okay, for normalized psi, we need it to be 1. All right, so okay, now in this case, let's write down a normalized psi. Okay, so this is similar to the calculation which you used to do for eigenvector normalization in matrix. Okay, it's the same thing. So we take this, we already have done this kind of calculation in previous lectures, just without the matrix notation. Okay, so this is what we have here: 5 iota, 2 minus iota. So this is a normalized psi. All right. So the C option says whether they are orthogonal or not. So we have psi and phi is equal to this minus 5 iota, 2 iota. So let's write it at a with spaces. Okay. So this is 3 and 8 iota. This is minus 9 iota. Okay. So if you take this inner product, what you get, this is minus 5 iota into 3 plus 2 into 8 iota plus iota into minus 9 iota. Right, so this will give you minus 15 iota, okay, plus 16 iota, and we have a 9 here. So this gives us minus, this will give you iota plus 9, okay, which is not equal to 0, right? We wanted it to be 0 for the states to be orthogonal. In this case, this is not 0. All right, now we can conclude that psi and phi are not orthogonal to each other. Okay, you could have reversed the inner product. You could have taken phi and psi instead. Okay, instead of this product, but you'll still get this result. All right, so they are not orthogonal to each other. Okay, now let's talk. Let's solve yesterday's problems. So let's have a look at yesterday's problem. So these were the problems. Okay, so let's like select them. Oops. So did you try the problems? Is anyone who has tried the problems? No one. Okay, don't never mind. We'll do it right now. Because you once have to solve these problems. We are doing limited number of problems just in order to, but these are enough for you to understand the concepts. Okay. Yeah, you have to, of course, be careful while solving a different problem. But in this case, see, it's given to you. All right. So let's see the question. So the question says a free particle of energy E collides with a one-dimensional potential, okay, square potential barrier of a height V and width this W, which one of the following statement is or are correct. All right. So tell me if you have not tried it, just try it right now. Okay. So this says the first one is E is for E greater than V. The transmission coefficient for the particle across the barrier will be unity. Is this correct? No, right? The transmission coefficient is for E greater than V is not unity. All right. So the first option is says E greater than V, and this says that T should be equal to 1. Okay, which is not correct. Okay, incorrect. We have seen in the derivation itself. Now, what about the B option? What about the B option? We have E less than V, and for this we have the T. Let's see. Let's not get the whole the big thing in this case. The whole transmission coefficient, which is a big factor. If we don't take approximations, let's assume that approximate for the situation, and that let's say that the potential, the width, and the barrier height is very high. Okay. Now this reduces to gamma W. Okay, and this T. Now, if this approximation gives you the same result, it will give you the same result. It will have a similar result in if you take the whole the T term. Okay, as we had discussed yesterday. Now, in the last lecture. Now, if you see this term, you have in the power you have you can write this gamma as 2m. Okay, V naught minus gamma E. Sorry, minus V E divided by h cut square. Okay, and with the width there. Now we have the gamma here. Gamma is equal to root 2m V naught minus E, all right, divided by h cut square. All right. So if you see, we already know the gamma. Now if you see this, if you see the terms, so if you see these terms, so this is it talks about the variation of T with respect to V and W. So we have a dependence here, we have a V dependence here, we have a W dependence here. So V is under the square root and W is not under the square root. All right. So in this case, the T varies. We can say that if we vary the width, the value of T changes rapidly. Then if we vary the value of V naught, because it's under the root, it's under square root. All right. So we can conclude that T varies more rapidly, okay, more rapidly. And for problems, I always keep telling you, just follow the recommended books. Okay, if you for JAM purpose, MSc entrance purpose, SC Verma is enough. Okay, but if you want for GATE and NET, you have to go for Jetley and Griffith. All right, then now there are advanced books. You don't use them. It's not required to solve all the problems in GATE and NET to get top ranks. Okay, even the toppers are not solving all the problems correctly, so you don't need to worry about it. You have to do maximum questions as much as possible. So V naught is the potential barrier height. All right, and W is the potential barrier width. All right. Now, this is the B option is, it says the transmission coefficient changes more rapidly with width and then with V. So this option is correct, right? So the B option is correct. And let's see what is given to us. If for E less than V, if V is doubled, the transmission coefficient will be also be doubled. So this is not correct, right? Because if you see this expression which we discussed right now, if you see this approximation of this transmission coefficient, so we had this situation. All right. So if we what it says that if we double the V, transmission coefficient is not directly proportional here, right? It's not proportional. The proportionality is not in that manner. Okay, if you write this down completely, so you can see from the above equation itself, but let me write it down again. Okay, so this is minus h cut square. This is W. All right. Now, if you double if you change V naught to 2V, okay, so the T will not change because T is this will be equal to minus 2. If you write this down, so this change is not like directly proportional. All right, so this will change the only the power of this thing, and this is not twice the this new T1, this T is this new T1 is not equal to twice of T. All right, so this means this option is incorrect. All right, now the final one, it says that the sum of reflection coefficient and transmission coefficients are always 1. So this is true. This is true. All right, so let's write it down here. Let me shift this a little, and we can write this last D option. So R plus T is always 1, no matter what. Okay, so this is true. So this is also correct. So the correct options here are B and D. Okay, so B and D are correct. All right. Is it okay? Were you able to note it down? Were you able to note it down?
Yeah.
All right. So next one is, next question is this. All right. So in this case, it says that you have a particle, you have a certain particle which encounters a barrier, and the tunneling probability is given to be e to the minus 10. So it's already talking about a tunneling probability. So we have to take the approximation formula for the transmission coefficient, which was approximately equals e to the minus 2 gamma a, or whatever the width is. So if mass is halved and the width of the barrier is doubled, approximate value of tunneling probability. So this was a very straightforward question. You have this format. So from the question itself, you know that what approximation to take. Okay, so this is e to the minus 10. All right. So whenever the product gamma, whenever the product gamma a is approximately more than or equal to 10, so you can use this approximation. If it's less than that, you have to use the tunneling probability formula. Okay, not the tunneling probability, the this thing, the transmission coefficient formula. All right, for E less than V naught. Now in this case, if you compare the powers, we have 2 gamma is equal to 10. Okay, and we know that gamma is equal to root 2m V naught minus E. All right, this is h cut square. Now in this case, the new gamma, let's talk about the new gamma. Okay, new gamma, which is, let's say, new, it becomes new. So we talk about new gamma, which is gamma 1. Now let's put the values which we have given. The mass is halved. Okay, so we have put m by 2 and minus v naught by minus e. Okay, and we have this thing. Now what it says is the barrier width is changed. Okay, so with the gamma is 1 by root 2. The new gamma is 1 by root 2 of the old gamma. All right, and we also have this now A1, the new width, is given to be twice the earlier width. So this implies that the new transmission tunneling probability is e to power minus 2 gamma 1 A1. Okay, if we write this down, so what we have is gamma by root 2, this is 2a. All right, this gives you e to power minus 2 root 2 gamma a. All right, so if we write this down here, now instead of this thing, we have e to power minus, now instead of this gamma, we can use this form, this result. We can use this result. Okay, we instead of 2 gamma, we can write 10, and we have finally this result, which is 10 root 2. Okay, so this is the answer which we were looking for. All right, so this is, say, if this is equation 1, if this is equation 1, all right, so this is 1, so this is by 1. All right, so this is the answer. The correct option is this B option. All right, so what we can do is we'll start in the next lecture. We'll start with hydrogen atom. Okay, so it will consist of both JAM and NET syllabus and GATE and TIFR just. Okay, so I'm doing the major topics, whichever is common. All right, and I'm planning to take a test after I complete this basic part, and I'll take a test, and then I'll select those students, and then if we are able to score well in that exam, then I'll go for the advanced topics. Okay, otherwise it's useless to teach you advanced topics if you're not able to do the good in the basic topics. All right, but the topics which I'm already covering, it will help you in all the exams. Okay, if you study it carefully and remember the things carefully. Okay, you don't need the advanced topics which only appear come in GATE and NET, and there too are rarely coming these days. Okay, the scattering problem has not been asked for several times in a row. Okay, and the perturbation is also a simple problem. So what I'm telling you, that spin is also the questions have been reduced. A number of questions have been reduced. The questions coming from these topics. All right, so planning, because those topics take a lot of effort to learn. Okay, so I'll take a test after I finish this the most important basic topics here. All right, then we'll go for the advanced topics. So I'll give you a time between some 15-20 days. Okay, then we can discuss about it. All right, so till I'll do the hydrogen atom, and then we'll do the photoelectric effect, the Compton scattering, the black body radiation. Okay, the wave thing, phase velocity, group velocity. All right, these are very important for all exams. Okay, we'll do that, and then we'll see. We'll plan the advanced topics later on. All right, so any doubts, any questions for today?
Sir, hello,
Yes.
sir.
Yes.
Sir, in the previous question, sir, where we had to normalize psi.
Yes.
Sir, I have doubt, sir. I thought like when we did inner product of psi, we got 30.
Mm-hmm.
Sir, so I was thinking like we will take normalization constant as 1/30 because we are expecting it to be 1 and it's 30.
No. The product is giving you 30. There's not single psi here. If you remember the normalization chapter, the lecture which we did, we were always dividing by the root of 1 by root of the normalization, this value, not the normalization constant. The normalization constant was always this thing. If you remember this, it was always summation ci mod square, or it was always 1 by this the value of this thing, psi and psi. This is always the case. Okay, we have already discussed this part. So it is not like, because see, in this case we have two psis here. It's an inner product of two psis. It's not just a single psi which is giving you this result, but we are looking for a single normalized psi. And of course, we always talk about a single normalization of this psi only. We do not talk about normalization of a inner product. Okay, we talk about the normalization of a wave function.
Okay.
Right. Yeah. Any other questions? Any comments? See, whenever you get a gap, whenever in any whatever preparation you are doing, please have a schedule, and please have a 1 week schedule. Please have a 1 month schedule, and also have a daily schedule. Before you wake up, you should have the schedule in mind. Okay, and there might be that okay, the class has been postponed, or the college there's something you have to attend. Then you can make accordingly the real time changes, but make sure that you have a minimum number of hours given to your preparation. So it's like if you want actually to get into these good institutes, then you have to put an effort, and that effort is huge if you start right now. Okay, if you have been doing already for last 3 months, then it's fine. But if you're starting right now, and still you have time, okay, and I won't say you'll have time after 1 month, but if you have a good memory, if you have good understanding, then you can do it that way. But if you are not, you think you're not able to do that, just start doing today itself. It's not yet late. Just start with that and focus on those topics, those subjects which you are good at. Okay, make them more stronger. If there is time left, then you can take up the smaller ones. Okay, but make sure you put focus on these big topics. There's quantum mechanics, electronics, mechanics, EMT. Okay, then you have thermostats. All right. So these are the major topics for any exam. For any exam you take up. All right, and for even for interviews also. They'll ask you from this. Okay, there are rare interviews where if you are going for say you want to do a PhD in nuclear physics, they'll of course ask you about nuclear physics, but that's a rarity. All right, they always check your basic. These are the basic things. And quantum mechanics, there's a advantage that there is a limited kind of questions that can be made. In mechanics it's huge. Okay, mechanics, there lots of problems can be made, but in quantum mechanics the number of problems are fixed. Okay, even we can predict the questions what can be asked this time. Okay, sometimes. So keep this in mind. Quantum mechanics is a very scoring subject. Okay, and if you follow these lectures carefully, revise, keep revising it, keep recalling it, don't forget any formula, don't forget anything. See, there is no excuse of forgetting. If you forget, you're gone, you're done. Even if you miss a single problem, there's 2 marks. All right, so if you miss that problem, then the rank difference will be huge. Okay, you can go from top 50, you can go up to top 200. Okay, so hundreds of ranks you'll be down in some cases, not always. So maybe in some cases 50 ranks, maybe in some cases 25 ranks. So you cannot make a mistake there. All right, and if you say that you are not able to remember things, you have to remember. See, it's the same thing. We as children we used to learn ABCD. It was difficult for us that time, but we don't think about it right now because we have practiced this so much. We have a memory of it without even remembering it. So how did we do that? We repeated it many times. We repeated it many times. There was no understanding. There was memorization. Because memorization is important. Without memorization, you won't be able to solve problems. Okay. Yeah, of course, understanding is matters. Otherwise, you won't be able to comprehend these questions. All right. So these are the important things. And there's nothing called no such thing as motivation without action. If you are studying continuously, if you are putting in effort, you are putting it consciously. Okay, it won't come to you subconsciously. You have to do a conscious effort, and slowly you keep on increasing the time and try to get remember things. Okay, and if somebody says you tend to forget things, uh, I do not know how to tell them this, that is a kind of a, you can say, a laziness or a procrastination. That is otherwise there's no other way you can get out of it. If you're thinking to build a career in physics, or in any field you want to build a career, you need a good memorization technique, and then understanding, of course. All right, without understanding, memorization doesn't is of no use, and without the memorization, understanding is of no use. Okay, so it's all complementary. All right, so thanks for watching and have a great day. All right.